Hello, this is Leo again with the fourth talk in this series. We're now going to Newtonian dynamics, and we called it the Forque Awakens. You'll see why. I'll have a brief overview of the talk. There'll be two types of lines that we need to talk to about. Stephen has already mentioned that. We're going to talk about moving heavy things. We're going to use forces, do a bit of differentiation. Well, maybe it's easier to show you the summary of the talk by a little scheme that I've made. So here we have hyperplanes that meet into a hyperline. These are the meet lines that Stephen was talking about. And they will determine the rate of motion, the velocities of motion, and the accelerations. They're of this type. And we will be able to connect points with the join operator that gives us a dual type of line, the join line. And this is the way that momentum and forces and torques are encoded in geometric algebra, and there's a duality between the two. So the talk is going to proceed as follows. We have basically done this part in the first piece of my first talk, where we talked about planes, meeting them with lines, characterizing motors with their exponentials, which are the rates. Then now I'm going to give you a little bit of algebraic detail of how the join lines are represented. We're going to put masses in motion to get the momentum. I will show you how forces and torques are unified. We'll do a bit about time derivatives, because obviously that is relevant to see how that is represented in PGA. And then we'll very quickly have the dynamics before we know it actually. Okay, so there were two types of lines. You can meet two planes in a line, and these planes can be parallel, and the line is at infinity. That's sort of the same thing for us. But you can also connect two points and get a line. And you can connect a point to a direction and get a line. And these are really of different types. This moving along a line is what we need when we talk about momentum. So we have a point and we have another point. We connect them by a joint product. It's slightly more complicated to define, and so I won't do it in algebraic detail here. The important thing to know for the dynamics part is that if you want to make the line from a point x that moves in the direction u, then this becomes the object, the algebraic element u dot x. Now we've seen that points are represented as d-vectors. They're the intersection of d planes in a d-dimensional space, 3 in 3-dimensional space. And if I take the dot product with a vector, I get a 2 vector in 3D, or a d-1 vector in general. And this really is a dual object to a BiVector, because I totally have d+1 dimensions, as you see here. So they're different objects. They're slightly confusing in 3D because they both come out to be BiVectors, but it is important for the goals that we have for PGA to recognize their difference, and it simplifies the code. Now, Stephen had a picture of the robot on the one hand and the floor plan on the other hand, where he motivated that some of them are points that generalize from 2D to lines in 3D, and other lines remain lines because they were the robot, or they become planes, just to motivate that we need both types of lines. This is another illustration of that same fact. As long as you get that, we can proceed. We need them both in our algebra, and we have them both. All right? So some of them are the BiVectors and the others are the dual BiVectors. Time to put in some mass. So when we have a mass m moving with a velocity v through a point x, then we're going to make a heavy line, a line weighted by the mass, but it's obviously a join line. The point was first here, and then it was, well, x plus x dot further. This evolves with a little bit of algebra to the formula mv dot x. Now mv you recognize, this is the classical momentum of the point, and x you also recognize, it's the point where it happens. But in geometric algebra, this element, this dual BiVector, this join line, contains both of these. It is really a geometric object that indicates both what happens and where it happens. And it turns out that that property of PGA really makes the formulation of the physics aspects a lot more easy than it is in the classical way. Well, at the end we'll compare them. So it will be an element of geometry and it makes it coordinate free. Now if we have several points, then we know that the total momentum should be composed of the momenta of each of these individual things. We will see in a few slides that in PGA, if you have something that moves by a motor, then its time derivative is a commutator product with the bivector of that motor. So, taking that as given for now, you see that we get a total formula here for the momentum, which depends on the rate at which something is moving. The spatial rate, in the sense of the turning axis, the shift axis, and everything, all encoded by this one bivector b. And this linear function of the bivector is called the inertia, the total inertia. Now you see that this map is rather special. I have taken a bivector, which describes the rate, the exponential of it is the motor, and I have converted it into a join line, which was a dual bivector. So the masses and their distribution, as encoded in this formula, define a duality map in the algebraic sense. They map a rate, a velocity, to a momentum. Classically, I always thought that velocity and momentum were the same, with just a mass thing between them. That turns out not to be the handy way of thinking about it. This inertia is rather unusual in its properties. You can, if you have two objects of which you both know the inertia, you can just add them to get the inertia of the total object. Whereas classically, these inertia maps, they do exist, but they are developed relative to the center of gravity of each of the objects, and you need all sorts of rather involved theorems in between to convert it to the total momentum relative to the new center of gravity. In PGA, that's all not necessary. Everything just adds. And the reason is that the position where you had it is encoded in the objects themselves. They are really, truly geometric objects that can be manipulated in geometric ways. So here's that summary again. We have two sides. We have a rate, a velocity, which is a bivector, which is a midline, and the duality map converts it into a momentum, which is a join line. And you can say that the rate is how fast things move is, and what the consequence of that movement is for the total movement is kinematics, depends on the geometry, and the P contains the masses and is for the dynamics, it depends on the masses. The map between the two is the inertial duality map, and it really is a dual thing. You can sort of see that when I represent the bivectors that I'm going to act on in something that has mostly the Euclidean elements and the infinity directions. Say if I exponentiate this, I get rotations around the origin. If I exponentiate this, I get translations anywhere. And you see from the sort of cross-diagonal form that it acts on these and it produces these. It really swaps these things. It makes meet lines into join lines. All right, so let's go to the forces. Now, we have seen momenta are lines because they're a point, and where the point is a little while later joined to each other. We know that in Newton's laws, the force and the momentum, the time derivative of momentum, are closely related, and indeed forces are also lines. So if I am at a location x and I feel a force F passing through that thing, then I am on the force line F dot x, exactly the same sort of form as the join lines I showed before. But there's something really interesting going on here when you look at the same force from a different point of view. So this force line F dot x was a force passing through the point x. Let's go and stand at a different point y And let's be interested in seeing what we feel over there from the force. Now you see I have this one object f dot x. I expand it using this formula that you may or may not remember from the second talk of what a general point looks like. I split that up because I'm very interested to know what I feel at y, and indeed I feel the same force F as y. But this geometric force thing automatically produces something that I would call the torque that I feel at y as an infinity term to preserve the geometric object that it really is. So because I'm standing at y, I suddenly feel both a force and a torque, but they are completely unified in the geometric object that is out there in nature that I am subjected to. Now, because the force and the torque are united, we call them forque to indicate that aspect. And so the whole dynamics in PGA will not require you to split these things in forces and torque. You can, if you know where you stand and you want to know what you feel there, you can do it. But nature develops independent of where you are, and the fork encodes that. All right, we're going to have to go to time dependence. So let's take an object x that moves with a motor relative to some standard object x0, and you know that that goes like this. We know that the motor is going to be writable as some kind of a BiVector that develops in time. And so this combination of forms then determines what the derivative of a motor is. There's an initial motor that I can actually encode in two ways. I can look at the world frame, so I take a pose of an object and I move it afterwards with this time-dependent element. Or I could say, well, start at the standard phase, put it in the right position and location that I want to do it, and apply the motor M0 to be where I am. At t equals 0, these are exactly the same sort of thing. But here I have moved in, let's say, the world coordinates, and here I have moved in the body coordinates. As I do the differentiation, why is this important? Well, because the geometric product doesn't commute. So if I do the differentiation of this term, I get a BW, and then the same thing that I had. And if I do this differentiation, I get the same thing I had, and then a B body frame. These are two equivalent ways of describing things, and for the rest of the talk, I will concentrate on this way because it leads to slightly easier formulas. But, it's a choice of convenience. All right. Now, we have an object x that was produced on an object x0 by a time-dependent motor. What happens if I take a time differentiation of that? Well, sort of the same thing. If I take the differentiation of this thing, I get the b of the motor out of there. And the rest remains because it's one of those exponential functions. It's b times the exponential. If I then let it act on this, well, that's constant. If I then let it act on the final term, then I again get the whole thing, but I get a b afterwards. And so whatever the motor was, I will always be able to write the time derivative of my x that is moved by a motor as my original x with a combination with the BiVector of the motor only. And the combination, that is the commutator product, is just an antisymmetric product of a combination of geometric products. So the BiVector of the motor completely characterizes at this level what the time derivative is. And so again, like before, we find that this set of BiVectors, this actually forms the Lie algebras of the motors, is what is relevant in this as a tool to describe how things move. Now, Newton simply said that the force is the time derivative of the momentum. Euler said something similar for the rotating motion based on torques. In geometric algebra, they are completely united in saying that the fork is the time derivative of the total momentum, and that will contain both the rotational and the translational aspects. I just don't want to split them anymore. That means we need the time derivative of this thing. We know that the momentum itself was the inertial map applied to the bivector of the motor. And what do we do when we differentiate? Well, we get a cross B. I just showed that on the previous slide because this is a thing that moves with the motor. But we're not quite done because the B itself may be changing in time as well. So we also need I on B dot. I is a linear function, so I can pass it through there. And this, surprisingly, is all. We now have fully unified dynamics. We have the equation F equals P dot, which we just derived. What are we interested in? Well, we want a differential equation for how the velocities change. So we want to isolate B dot. That means I have to bring this to the other side and take the inverse of the inertia map on this. So this enables me to say that if you give me the forces and you give me the mass distribution that I want to move, then solve this differential equation to see what its velocities are. And then once I have the velocities, I have this equation in the body frame that allows me to integrate the motor from those given velocities. So this is the dynamics. There's really mass involved here, and this is the kinematics. And when you write this out, surprisingly, this contains all of the Newton-Euler dynamics, the angular momenta, the linear momenta. All these things are hidden within this if you want to unpeel them, but you don't need to unpeel them. You can immediately apply this equation. And here you see me doing it. So this is, again, one of the Ganja demos. We have a heavy object under gravity on a hook spring with some damping. And it is directly implemented in the way that I just described. So when you look at the code that Steve will also demonstrate in session 6 today, you'll see that he will define the gravity, define Hooke's law, define the damping, all in terms of compact join lines of geometric algebra. The total force is then something like this. And the whole equation is that the state of M and B changes by the equation I just showed, where here this bang is, this exclamation point is the duality of the object. And you just solve the equation. And so here I'll show it again. No, this is a very realistic looking motion. Well, yeah, where it deviates from reality is by the integration step, but the equations are exactly right to be the physics. So here's the overview again that I showed in the beginning. Momentum and fork are both join lines. Rate and acceleration are both meet lines. There is a duality map between them. If I give you a force and I give you the mass distribution, then I know this and that. And by navigating this diagram, by these two equations, I can get the ultimate motion. And this is not just algebra, this is actually the program to do it. So, in 3D PGA, in the dynamics, the BiVectors and the dual BiVectors both coincide to be elements of grade 2. This takes a while to be careful with your formulation and pull it apart. It was actually when we looked at how we would do dynamics in 2D that it became most clear that they are really two different objects. It may be that this confusion, which, I have a PhD in physics, I have had this classical mechanics, but I hadn't had this clarity in seeing what made dynamics tick. This happens for the first time, this eye-opener in looking at the 3D PGA. And not only that, it really makes it dimension independent. Stephen will actually live program how you do n-dimensional dynamics of a cube on a string under Hooke's law. All right, so to conclude our PGA tour then, let's look how classical mechanics is embedded And here you see the total picture. So all we have in PGA is that we are talking about the bivector rate of a motion, the body properties encoded in the inertial duality, and then via the momentum couple it to the force. And these are all the symbols we need in the equations, and as you saw from the demo, we can encode and solve these equations. How do you do it classically? Well, you have a fixation about wanting to see rotations as different from translations. That is something that you should have forgotten after the first two presentations of today. Translations are rotations too. They're just rotations about a point at the line at infinity. That's a unification. When you do that unification, you no longer have to say, well, this momentum occurs at this point, and if I go to another point, then I need transformation laws, some of which describe the inertia, but is it the change inertia around the new points? No, everything is just I of B. You never have to look at the right side. Similarly, when you look at the momentum, you don't have to say there is a linear momentum and there's an angular momentum, and if I go to a different place, then I keep my linear momentum, but my angular momentum changes because I'm offset of that place, and one of them is relative to the centroid and the other one is to the origin. It also, again, doesn't happen. The magical thing is that if you dot the classical momentum with the point where it happens, and you wedge the angular momentum with infinity, the plane at infinity, then you will get an invariant object, P, which you can immediately integrate without having ever to make that distinction. And yes, linear momentum sort of couples to the force, and yes, angular momentum sort of couples to the torque, but those are unified as well in exactly the same way, and that's why all you need are things on the left. So, very recognizable, and a great pity that we haven't seen this before. PGA, I should say, is not the only framework in which these things are united. The important thing is that you have one six-dimensional space in which the things come together, and there are two things, screw theory and spatial algebra, that do similar things, but they really see it as a handy little trick, algebraic vector space that you introduce to make things work. We have seen that once we are in the space of planes, we are in a four-dimensional space for a 3D encoding, we automatically have a bivector space that is already of the six-dimensional nature, and all the elements and their integration are given for free when we do that. Moreover, if you take the screw theory and spatial algebra approach, you're only talking about motions and never about the objects, except in their inertial properties, whereas we see that by the meet product and the joint product, we actually have encoding of the geometric primitives that our motions can work on. So we get a fully integrated framework, which of course for applications in simulations and computer graphics is very nice, that they live in the same space. We have also seen that we can just as easily do d-dimensional kinematics and dynamics, as Stephen will show you in the demo, whereas the screw theory and the spatial algebra are very, very specially tailored to the three-dimensional case, because their whole representation is hard-coded. All right, well, also here we have demos. I think it is nicer to see Stephen at work actively in producing them so that you can get a flavor of how that works. We have also modeled contact forces in the same framework. All of these are, again, clarified by distinguishing the meet lines and the join lines. And a message from our sponsor. If you really want to be part of the PGA crowd, then of course you should wear your belief on your sleeves, and we provide the tools for that as well. All right. Thank you.